So here we go. Give it a chance to catch up. This is a live coding session. It's working on an idea that's been rattling around in the back of my head for quite a while for an optimization that could be done in raptorjit. The optimization is called sealed tables. I'm sure it's nothing original, but it might be very practical for some of the applications, some of the kind of code that we write to speed things up. So what I want to do today is take a bit of a loose brain dump on the whole context of what it's all about, and hopefully thrash out the context and then be able to define the problem a little bit more crisply. And if there's time, we can also take a look at some of the code that's going to be impacted, if it looks like this is something that we can implement. So let's dive right in. I'm gonna, because this is another topic, so I've been doing live streams on other features like on Studio and some perf tool stuff and this kind of thing. So I have a lot of irons in the fire in my in the topics that I'm live streaming. So I'm going to start doing a little bit of basic tracking on these so that we can come back to them whenever it seems like the right time. So these days GitHub has a feature called projects, which is basically an inline Trello board. So I'm going to make a project to keep track of the work that we're doing on the table, a sealed table optimization. Create a project, and we will make a to-do list. We will make a doing list for whatever it is that we actually have on the table, and we'll have a done list. So we can just keep adding things here, and when we come back to this topic on a stream, we can just pick the latest thing off our list or whatever it was we were in the middle of doing and just continue. So I just say brain dump on context is the first thing we want to do. Then we want to define the problem, and then we want to review the impacted source. And then we want to do the rest. So just to not give the impression that that's everything that needs to get done. All right, this came in the opposite order than what I expected. So let's just flip them around. And then we have our to-do list. And what we're doing now is brain dumping the context. So if I get interrupted or we run out of time or anything like that, then we'll come back to this list next time we'll remember where we were at. So brain dumping on the context. So the basic theme of this optimization is that we want to find some computations that are being done at runtime as the program runs, and we want to move some of them to be done instead at JIT-compilation time. So it happens, so instead of doing it every time a function executes or a loop executes, we would do it every time a function or loop is compiled, and that might drastically reduce the amount. And pardon the sound of a dog drinking his water at my feet. So I'll just whip up a little example. So here is our studio where we're going to do our experiments, and we're gonna write a raptorjit program. Studio is a front end to a lot of different programs. We have to tell it that there's raptorjit code that we're writing, and we're going to define a module as a global variable. It's going to be called mod, and it will start off being an empty table, and then we will say mod.func. We'll define a function called mod.func. Is going to be a function that takes a number and returns the number plus 1. Very simple. There is a module assigned to a global variable called mod with a single function called func. Let's call that in a loop that will be compiled. So a loop that runs 1 billion times, and what will that loop do? It will pass the loop index. You will call the function with the loop index. So this is Lua code. The thing to know here is that semantically, when we write mod here, we're referring to a global variable. Global variables are a hash table, so this is a hash table lookup in the global variable table. And then when we say function, we're doing a hash table lookup in the module table. So in principle, just looking at the source code here, on each pass through the loop, we're doing a hash table lookup to get to find the module Then we're doing a function name lookup in that module to get the code that we should run, and then we're finally passing in the loop index and doing the increment. So I think if you were a Lua, like a non-JIT Lua programmer, you would look at this and you would think, well, this looks very inefficient. You can't use globals like that. You have to cache things, and you would do all kinds of horrendous to me workarounds. But what we want to do is make code like this compile really well all the time. That's our basic goal. And what I'm going to try to demonstrate now is that it compiles really well some of the time. And so the problem that we have with the sealed tables is to go from compiling well some of the time to compiling well all of the time, so that we can always write code like this and never feel bad about it. So let's run this program. Hope I didn't make any syntax errors. And we get, widen that a bit. So it ran, we get a profile with 419 samples. So we can, normally with raptorjit, we normally use profilers to find the code that we're interested in, because if in this case it was a small program, but if the program is even slightly non-trivial, you can end up generating quite a lot of code. It's pretty handy to use the profiler as the way to identify what's interesting and what's not. So let's see how this loop over here compiled. These are the byte codes that it ran, 9 odd 8 byte codes. This is the intermediate code that was generated by the JIT. This is kind of like a high-level assembler code. This is the level of abstraction that we normally use to understand what the JIT is doing. Each one of these intermediate representation instructions assembles to a small number of x86 instructions. So the relationship between this IR code, IR is intermediate representation, the relationship between the IR code, which is high level, and the x86 code is similar to the relationship between x86 code and CPU micro operations. So each of these instructions breaks into a small number of machine instructions, and for our purposes, we can mostly think in terms of the IR instructions. But anyway, let's look at the visual version of that, because it can be a little bit hard to put this together. So if we put a visual kind of a facade on this, then it can become more tractable. So what we want to do now is understand this picture, and we're going to do it in small pieces. So the first thing I want to say is that there's this loop thing, which is delimiting a kind of a horizontal line, because what we compile is a loop. Remember the source code over here. It's this loop that we're compiling. So we do a billion iterations, and each time we call via a global variable, we call a module and its function, which then increments the loop counter. So what we have here above this loop is the code for the first iteration of the loop, and then what we have below is the loop optimized code, which is what runs for the later iterations. So we did a billion iterations in total. So on the first iteration, it ran like this, and on every other iteration afterwards, it just ran with a smaller amount of code. So step by step, let's zoom in a bit. If we zoom in on the loop optimized code, what do we have? So each of these colored boxes is an instruction. It's the same. They correspond one-to-one with this listing that we have over here. So what we have, we add a value that we pulled from the first iteration of the loop. So something that was already calculated on the first iteration is already in a register. We take that and we add 1 to it, and then we check if the result is less than or equal to 1 billion. So this is checking for loop termination. Well, and this is really a so-called guarded assertion. So so this asserts that the new loop index is less than or equal to 1 billion. And if that assertion fails, what it means is that it bails out of this machine code, and it's an exception of sorts. I'm telling the runtime system that it's finished running this block of machine code, and it's time to continue. So that's how the loop terminates. But in all of the first goes through, it adds 1 to the loop counter, and it asserts that it's less than or equal to 1 billion, and that will be okay, and it'll loop. And we also have this this phi, and what that is an update of another value. So we see here we imported a value from that was done previously. Oops, let's zoom out a bit there. So the add imported this value here. It was calculated in the first iteration of the loop, which is the current loop index, and then what happens is that on each pass through the loop we replace that value. So the phi says that we take the result of this coming in here to the phi, and then the phi ships that out and kind of overwrites this value here, so that this is how we thread the current value of the loop index through the loop, how we connect things together. It's a little bit like a monad if you're into that kind of thing. Anyway, the thing to realize here is that this is kind of the code that we want. We're running a loop that just actually all we're doing here, I didn't put a side effect in there anywhere, so actually I'm going to update the example. So this is actually simpler than what we want, right? This is compiled into an empty loop. So the actual call to the function has been optimized away, which is a little bit fancier than what I actually want to demonstrate. So let's change that. Let's assign a global variable z to be this. So we have a side effect in the loop, and we expect to actually do some work. So let me run that again, and we'll get some slightly less trivial code, which will be a blessing and a curse. But anyway, in we hop. So now, this is the code that we had before. This is incrementing the loop index, checking for termination, and passing through the updated loop index for the next round through. And then here we have an addition. It's an add with overflow. So this has been compiled. It's been compiled on the assumption that this is an integer that can fit in a register, and if that assumption is violated, then it's gonna bail out and you have to use different code. This thing gets converted to a Lua number, which is a double float, and stored in a hash table. And what we should find is that in both cases we have the previous value of the loop counter there, and here we take it and add 1 to it and store it in a hash table, which is this code here. We add 1 to it there, and we store it in a global variable, which is to say a hash table entry in the globals table there. And okay, so this is actually pretty efficient code. What we're seeing here. So each time we go through the loop, we bump the loop counter, we check for termination. We also bump the we also call our function to increment mod.func to increment the loop counter, and then we store it in a hash table. So if we compare this, so this is the code that we want to have. Basically, there's nothing objectionable here. Particularly, this looks actually really nice. The thing is, the code up here is a longer story. So for this simple example, we actually don't have a problem. This is a fast program. This is very kind of tightly optimized. This is great. The issue is that if the loop optimization doesn't kick in for whatever reason, and there are kind of a lot of reasons that it can be either not apply or be much more limited, then what we actually run is this code up here. So we have to actually concern ourselves a little bit with all of this funky stuff. And the first thing we need to do here, so the idea with the loop optimization has taken this big complicated block of code, and it's minimized it down to this smaller amount by recognizing that certain bits of work that were done on the first iteration do not have to be repeated on later iterations. So it's considered to be loop invariant. It doesn't change from one iteration to the next, and it's done this very successfully. So the idea of the table sealing optimization is going to be to have the same effect of cutting out a lot of instructions, but in a different way that's more broadly applicable, and particularly can apply in cases when loop optimization doesn't. So it's going to be another another way to achieve the same thing, so that we get a bit more, we can depend more on this work being optimized away. So let's just briefly look at what this work is, so that we can talk about why the loop optimization was able to skip it on the subsequent iterations, and how we're going to potentially skip it with this new sealed table optimization. So if we look again, we got this loop border here, where everything below loop is the optimized later iterations, and everything above is the less optimized first iteration. And the code here is basically the same as the code here. So on the first iteration and on the subsequent iterations, the thing that we have in common is we always need to add 1 to the loop counter. We always need to check for termination. Let's just zoom in ever so slightly. We always need to add 1 to the loop counter, there and there. We always need to check for termination, there and there. We always need to call mod.func, which does this add and a convert and a store into a hash table. The hash table store is over there a little bit. So this is the same. The difference is that on the first iteration we do all of this other stuff too, which is like a lot. So most of the instructions, what are we going to say, like 2/3, 3/4 of the instructions are extra work that needs to get done on the first iteration, but doesn't need to be done later. So the question then is, what is all of this work, and is it really needed? Well, actually, I have a newer version that does a better job of decoding these. Provides a little bit better information here. I didn't quite have time to merge that topic branch to where I'm working now, but we'll just interpret this anyway. It should not be too bad. So this is the overhead of accessing. This is the overhead of this global lookup kind of a thing. So it starts with a stack load, and what this instruction is doing is getting the table of global variables and loading that into a register. S load is a load of a value off the Lua stack, and we can always find the global table there. Now we're doing a field load. This is when we take some Lua, the internal representation of an object, we access some internal field, and in this updated version that we'll see next time, it'll say which field it is, but we can kind of we can kind of look around, work back from the way things are used. So what we have over here is this is checking the size of the global variables hash table. It's saying that the hash table mask should be 63. So the current size of that hash table should be 64 entries, 64 buckets. And so this is a guarded assertion. So the thing is that we're gonna, over here, we're going to wait, what are all of the other things they're doing? So we it would be a lot easier if I had the one that tells us which fields they are. So this is loading the bit mask that we mask the hash value with. Find a bucket. It's asserting that that has to be 63. That's to check if the global's hash table has grown since this machine code was generated, in which case this machine code couldn't be used and we'd need to bail out and do something else. Again, it's probably easiest to work our way up from the bottom. Here we're referencing hrefk, constant hash reference. So we if we know the key that we're looking up, and we do because we're looking up the key mod in the globals table. So we know that the key we're looking up is mod, and if we also know over here that the hash table is 64 entries in size, then we can figure out exactly which index into the hash table we need to look, because because we already know the key is mod, so at compile time we've already hashed that, and we've masked the hash down to suit a 64 entry table. So this is referencing the slot inside the hash table where we know the mod is going to be, and then from there the result of this is the table for our module. It's this. So we've done our first lookup there, and now what we get from that hrefk is the module table. And there we want to basically do, well, sorry, we get the slot there, and then we do the load from the slot, and then we get the actual object. And from here we want to do the same thing. So this represents the mod table. Now we want to get func out of that. So we check, like we did over here, we check the size of the hash table. We check that we load the hash mask field from the table. We check that it's 1. So this machine code has been generated specifically for the case where that hash table has 1 entry, and this is checking that assumption holds. And then over here we do the same. We reference the hash table with a constant key, which in this case is func, the string, and the result of that is the address of a slot in the hash table. We do hload there, which gives us the function, and we can see in that tooltip that it's a func, is the type coming out of that hash table load. And I guess we won't go into it a lot at the moment, but it's kind of interesting that Lua is a dynamically typed language, but this intermediate code, assembler-like code we're seeing here, is actually statically typed. So that's a function that we pull out of there. And then interestingly, when we get this function out of the hash table, all we do with it is do an assertion, an equality assertion on it. We never actually like call it, so to speak, which is significant. Just thinking about the way to order these thoughts. So basically, if we just look at all the sum total effect of all this extra code, I mean, so again, on the left we have the actual work that we want to do, the bumping the loop counter and calling, doing the +1 from our function call and storing that, and everything on the right is extra work. So what is all of this extra work? Why do we have so much code there? And you can kind of work your way up from the bottom to see basically all of this work was done in order to safely ensure that the function that we are calling is the one that we think. So all of this is to just go to the globals table and pull a value called mod, which is also a table, and then to go into that and pull a value called func, which is a function, and then to not call that function, not do any kind of a branch or anything, just to make sure that that function is the same function. So this is it's an identity test on that function to see that this is the same function that it was when this code was generated. So the point of all of this is just so that if we would change the value of mod.func, if we would redefine that function, that the code would understand that. It wouldn't keep calling the old version. It would do all of this loading, and it would get the current value of mod.func. It would compare that to what the value was when the code was compiled. It would see that they were different. It would say, this machine code is not valid anymore. We need some new code, and this guarded assertion would fail, and it would exit out from this trace. So that the entire point of all of this stuff is just to detect when that mod.func function has changed, so that we can invalidate the machine code and and branch off and generate some additional code for the new situation, for the new value there. So we're going to come back to that in a second, but just to illustrate why all we do is check the assumptions here. If we look over here, again, there's no function call anywhere here. The function calls don't happen at this level. You don't call functions. You inline functions. The JIT inlines every single line of every single function. It never, ever, ever makes a function call. So what that means is if at the Lua level you're calling a function, then when you're generating this code, you see which function is, and then you inline all of the contents of it, which in our case is just this add 1 to the argument, convert it to a Lua number, from an integer to a Lua number, out of a register and ready for the heap, and then store it in a hash table. You just inline that, and you add this extra funkery to make sure that if the function changes and your inline code is not correct anymore, that it won't run, that this will bail out. So basically the reason all of this exists is so that we can safely redefine mod.func. And I mean, so is this a problem? It's nice to be able to redefine things. That's kind of one of the fundamental properties of dynamic languages, late-bound languages, that you can defer a lot of decisions to runtime. You can redefine things. This is something that's used to great effect in a lot of languages like Lisp and Erlang, and these ones, it's completely standard fare to redefine code, load patches, and everything while the application is running. It's a cool feature. But what's the cost? And in our case, in this specific example, the cost is almost nothing, because again, if we zoom out, we have this funky loop optimization inherited from LuaJIT, which says, okay, we're going to do all of this work on the first iteration, but we're not going to do it on the later iterations. So this loop runs 1 billion times. It's only the first time, first compile time anyway, after it gets hot, that it actually does all of this. So from a performance perspective, in this example, it's completely irrelevant. It's been amortized 1 million times over, and that's the reason that happens is because the compiler has inlined everything, is not calling any unknown code. If any of these assumptions if anything would happen to change, to change the value of mod.func, it would have to be in here, because we've inlined all of the code that's running. So if this is the only code that's running, then obviously nothing's happening to the hash table. So we can say safely that, yeah, sure, this all holds on the later iterations, because we know that nothing has happened that could cause it to change. There's no other code is running except for this. So that's really, 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 really cool. But the tricky thing is, and I don't really want to go into it now, the tricky thing is that it's not always as neat and crisp as this. So the loop optimization works very well when you have a loop that doesn't branch and doesn't mix types. So if you have a lot of if then else, and in practice you're taking a lot of different branches, and your control flow within the loop is a bit more complex, or you have nested loops and that kind of thing, then basically loop optimization is not always there. And in the worst case, you can end up doing this all the time when your code is running, and that can have a really kind of major impact on performance. So in this specific example, loop optimization has fixed everything. It's fantastic. It's awesome. But in practice, you can't always depend on it being that way, and you also can't explain it in simple enough terms. You can't just write a golden rule of how you should write your programs such that loop optimization always kicks in, because it's just a bit too specific. So it's a long story to explain exactly how to know when loop optimization is kicking in, and even when you know, it's very, very difficult to actually apply it, or impossible to apply it to every situation, because you want to have nested loops, you want to have unpredictable branches, you need to do all of these things in realistic programs. So loop optimization just isn't the whole story here. And it can be a bit tricky, because if you just write a program like a little micro benchmark or a test, you probably see this wonderful performance. You think, okay, well, accessing globals and modules is free, hooray! And that's not the whole story, and it is a bit tricky. So what I want is for that to basically be the whole story, and I want to. That's what this whole optimization is going to be about. And before we talk about the idea of optimizing this, let's just look at what people do as I understand it, like normal Lua coders. So I don't come from Lua background. My first Lua implementation that I've worked with is LuaJIT, so I'm completely used to the JIT. But a lot of people are accustomed to not having a JIT and not having any loop optimization or anything like that, and never being able to get code like this to run fast. So what they would do is like this. As I understand it, they would say something like local mod_func is mod.func. So they basically create a local variable to represent a function that they want to call, and they cache basically they do the global lookup here and cache the result in a local variable, and then instead of calling mod.func, they call mod_func, and they basically do this for every function of every module that they want to call. And for me, this is just like, wow, is this like Java or what? Like, is this this level of boilerplate just totally blows my mind. But anyway, let's have a look at how that compiles. I haven't tried this just out of curiosity. All right, wasn't drastically much. Okay. There's interesting. So this is where this is the mod.func has now become just to load the function from the stack and do the assertion. So a lot of our hash table stuff is collapsed there, but we're still doing this assignment to a global variable. So we still have a hash table lookup over there. So I guess if we would stop using a global for Z, if we would also say local Z, try again. So now we have a much smaller program, right? And it's not that big of a difference between the first iteration of the loop and the later iterations. So this is the code that we want to have. This is definitely the code that we want to have, where basically the difference between the loop optimized path and the not optimized path, so we can say the slow path above and the fast path below, it's not that much difference. So it's nice that we do this extra optimization, but it's not really there's not really a problem here before. So the optimization goes from being something completely critical to making the program run okay to being just something that's nice to have. And I don't even know how to discuss the idea of doing this level of boilerplate where in every source file for every function of every module you want to call, you cache that locally. And people do this, and that's fine for them, but I'd rather burn in hell. So this is the compiler's job. This is not the programmer's job, and I don't think I'm morally outraged at the idea that we're gonna reward programmers for generating this kind of boilerplate by making their programs run faster. I think that's just totally not cool. So there's the context. There's the value proposition for some kind of an optimization that would give us this performance in a nice, simple, easy way, without having to end up with hundreds or thousands of lines like this in our source files, done purely to kind of take away. Well, I mean, what the other thing here on a fundamental level is what we're doing here is we're switching from being a late binding language, a dynamic language, to being an early binding language, which is more of a static language, because this runs once, right? So the first time we load this module, we're going to get the version of mod.func at that time, and that's going to be kind of frozen there. So if we would go through and we would update mod.func, we find a bug and we load a patch or something, that's not going to be visible because that ship has sailed, so that the original value has already been cached in weird and wonderful other parts of the program, and that's a legitimate thing, and for a lot of programs you probably don't care, but this is also sacrificing one of the distinguishing features of a dynamic or late bound language, which is that you can change your mind about things at runtime. You can change all this stuff. So, the actionable thing here is there is an assumption here that mod.func doesn't actually change in any kind of an interesting way. So the value the mod.func has when we load the code is it's fine to cache that and keep on using it. That's the kind of assumption behind this style of programming. And it doesn't need to be strictly the case that it never is allowed to change. It just means that if it does change, it's going to be a bit complicated, right? So if we have a program that's doing all this caching, and we do want to be able to change things, change the values of our modules and functions, then we need to do it in a careful way, or we need to live dangerously. So if we change the value, of mod.func, it's going to be, we're going to have to scratch our heads a little bit to think about what the implications are of that, and whether the new version or the old version is going to run in places, and whether whether that's important and whether we what lengths we're willing to go to. Anyway, let me now tell you what the sealed table optimization is. Well, let's take a break for 5 minutes, and then let's come back and talk about what we actually want to do. And that's also going to be a little bit of a brain dump. And then after we've brain dumped now about the context, we're going to brain dump a little bit about the rough idea for what we want to do, and then I think we're going to try to just write down a problem statement before we get too carried away. So back in 5 minutes. So coming back, now we had a pretty good look at the kind of code you get when you access, when you call functions of modules, and the way that's impacted by whether you cache the module object and the function object in local variables, which is popular in the Lua universe, but kind of taboo in my worldview, or whether loop optimization kicks in. So what we kind of found is that if we're going to be referring to globals, then we're pretty dependent on loop optimization to cut out a lot of work. And the problem we have then is that it doesn't always do so. We want to invent a way to make it do that. But actually, it's also worth just reflecting that this is much more general than just calling functions. So I've presented this as a way that we can just efficiently make function calls to other modules, but it's actually a really general thing. Anytime we want to do a lookup in a table of something that doesn't change very often, do we want that to be cheap or expensive? So if we have a mechanism that can allow us to say, for this table, I want to optimize reads at the expense of writes. I want to say, for this table, I want reads to be cheap to the point of being practically free, and in exchange for that, I'm willing to make writes more expensive. That's the basic idea behind this sealed tables optimization, and it's potentially useful for a lot more than just modules. It could be used for any data that is read much more frequently than it's written. For example, configuration data. If you have a server running and you often can reconfigure it once a day, for example, then instead of you might do 1 trillion lookups on the configuration data, between updates, and that might not be necessary. You might be able to just make all of that disappear, and that's the kind of optimization that we can do in a JIT compiler, because at any time we can recompile. We don't want to do it all the time, but once a day is quite a realistic kind of thing. So then the thing that I find interesting there is now we're getting into the realm of optimizations that are only possible, in my mind, with a JIT compiler. So things that we can kind of actually think about how we can beat C. People writing programs in C, they already got their machine code before the program starts. They're very limited. They have to anticipate any ways that they want to be able to specialize the code based on the configuration. If a configuration value is 64 or 128 or whatever, there's a lot of potential here. I find it very interesting that we can potentially do optimizations that are impossible in other languages that we're competing with, like C. So let's dive back in. So let's sketch what a sealed table would look like. So the idea with sealed tables is, instead of doing this, what we would do is when we have a table that we've created, and now we say it's in pretty good shape, we're pretty happy for it to be used as is, then we're going to seal it. We're going to say seal mod. This says the mod table we're pretty happy with the contents. We don't expect to change. We expect that we're going to be accessing them a lot, so we want to optimize the lookups, but we don't expect to be changing them very often. So we're willing to take a hit on updates, and we could also seal the globals table, which is called _g. So if we would do those two things, then our mod, we wouldn't have to do this hack with shadowing the thing. We could just refer to mod func, and then we would be looking up mod in the sealed global table, and then we would be looking up func in the sealed mod table. So we would be doing two lookups in sealed tables, so all of our lookups would be sealed. And then, then if we were doing a store into the globals table, it would be really bad, right? Because we sealed the globals table, we said that we're not going to be updating that very often. So actually, we wouldn't be able to do that. We need to put that somewhere else. It doesn't solve the case of doing updates to the globals, which we happen to have in this example. So it's still not going to be solving everything in the universe. Anyway, the specific idea is that when you seal a module, when you seal a table, what that means is that the JIT compiler will, when it's generating the machine code, it will do the lookup as usual, but instead of generating machine code to then redo that lookup each time, it will just inline the value that was in the table at the time the code was recorded. So basically it treats all of the values as invariant. So whatever it got, whatever object was assigned to the global variable mod when the code was generated. We're going to assume that mod is the same table, and when we do this mod.func lookup, we're also going to assume that mod.func is not changing, and we're not going to generate any of those safeguards in there. So again, if we just run the kind of slow version of the code again, and let's actually just run it with just run it as we did originally. So, you know, when we compiled this the first time, and we're just going to get the same code back again now, we got, looking at the generated code, we basically got two things. We got, look at the one at the top. On the left, we got the code that we actually want to run, that is the work that that we're doing in our loop. You know, it's incrementing numbers and checking the bounds, storing them in places. And then we've got a whole lot of other stuff which is just checking lots and lots and lots of assumptions that need to hold about whether there have potentially been any changes to any external values like mod and func that we might see. So we're going to just take away all of this code when we're doing lookups on sealed tables is the idea. So when we do a lookup in the globals table to find mod, we're just going to take, I mean, these are just checks, right? This is just checks, so we're just going to stop checking those things. And then the code over here is all we need to actually get the job done. So we're just going to take away all the safeguards and all of the checks. And that's going to be fast because that's the redundant work that we want to avoid, so that's fine. And we're still going to make it safe, but we're going to do that with a separate mechanism. So on the one hand, when the JIT encounters a sealed table, it's going to just completely remove the lookup in the generated code. It's just going to assume that whatever value it got at the time the code was being generated is the same value that it will always get, and the machine code generated is going to be completely dependent on that. And what this means is that any time we make a change to a sealed table of any kind, we can't trust our machine code anymore. That's just how it is, right? So the machine code is correct on the assumption that all of the sealed tables are invariant. So provided we're not touching our provided we're not changing our sealed tables, there's nothing to worry about. But as soon as we do change one of our sealed tables, we don't have that invariant anymore. We can't be certain that the code is actually using the latest versions of everything. So what's going to happen is that when we do a write to a table, we're going to check if that table is sealed, and if so, we're going to flush all the machine code and re-record it. So this is something that a tracing JIT does. So the idea, since back to the Dynamo paper where it all kind of comes from, is that if your workload changes in any significant way, then you throw away the machine code you have and you regenerate it. It generates some new ones, and this is the advantage of having a nice fast interpreter, that it's not that expensive. You don't want to do this constantly, but if you would do a configuration change on a server application once a day, for example, that's kind of reasonable kind of a time frame. Or if you would load a patch, if you find some really awful bug in some function and you want to load a patch to replace it, it's okay in these situations to regenerate your machine code. That's all right. So at least in the kind of use cases that I have in mind, doing kind of server software, it would be pretty nice to be able to declare that certain things like modules, all the library functions in all of the modules, and maybe even most or all of the configuration data in the application, to say this stuff, the JIT is allowed to very, very, very aggressively specialize on the current values of this information when it's running, because we're expecting to very, very, very frequently reference the library subroutines, and we're also expecting to very, very frequently reference all of the configuration data that we have. We're not expecting to change either of them very much. So we'll only change the modules when we load a patch to hotfix a bug. We'll only change the configuration data when we actually want to make some change to the application configuration. And if we can put some kind of a reasonable frequency on these things, once a day, once an hour, some reasonable bound, then probably we're going to be happy with making the trade-off that we get the fast reads at the expense of a hit on the writes, and this will pay for itself. And a nice bonus there semantically is, whereas the Lua programmers would be shadowing all of these things, but in doing so you kind of lose the ability to do things like patch the system, right? If everything is cached all over the place, then it's going to be a hard problem trying to do any kind of patching, like the kind of patching that an Erlang programmer or a Lisp programmer would consider completely routine, would just not really be possible. You actually would be losing a lot of, from my perspective, losing a lot of potentially interesting benefits of a late bound dynamic programming language. So I think that the code we're going to end up with, where we just use we just reference globals and we reference values in tables generally, without thinking twice about it, and we just when we've done constructing a table that we know shouldn't change for a while, should have a low frequency of writes, we're just going to seal it. If it's important enough that it matters, if it's something that's going to be referenced often, like subroutines and globals, then we'll just seal those, and if we do write to them, that's fine. And the new values will propagate instantly. There won't be any kind of caches that hidden caches that we need to find and separately invalidate, shadowed inside other modules. It will just flush the machine code. All of the cached values will be in that machine code, so it'll be gone. So as soon as we flush the machine code, all of our caches, invalid caches, are flushed, and we spin up new ones. And as long as we are only flushing at a reasonable interval and in a predictable way, then we're fine. So that's the idea. That's the idea for the sealed tables optimization. It's to add this seal built in, takes a table as an argument, and it optimizes everything there. And I should say at this point, I'm sure that nothing I'm saying anywhere in any of this is original. I know that the word sealed, I know this is something that exists in Dylan, and I know also specifically that Thomas Franson in the UK has done a thing called read-only tables, which, as far as I understand, is almost the same idea. I think his tables are immutable. So this is not some great invention of mine. This is just me thinking about how I've been too dependent on loop optimization in the past. I don't want to depend on loop optimization to always have to eliminate all of my table accesses, because I know that it's not really able to do that effectively for all of the interesting control flows I have in realistic programs. Maybe it kind of does a good job in micro benchmarks, but that's a problem. If you have a JIT compiler, it can be very good at special cases, so it's very dangerous to generalize from micro benchmarks, and I resist the urge to do that as much as possible. So I don't want to depend too much on loop optimization. I also don't want to do what the Lua people do with all of this manual caching of things, because I just I won't comment further on that. So we got to fix the compiler. That's where we're at. And if we fix the compiler, then everything is good. So that's all the idea that's been rattling around in the back of my head. That's all out on the table now. It's all swapped in and out there. So now, what was our next step? It was, I believe, to try and... So brain dumping on the context we have done. Now we're going to try to define the problem. So now we're going to try and make a succinct description of what is the problem. Well, no, you know what we're going to do? We're going to pull up, was it Leslie Lamport's famous Lamport define the problem? Didn't he... Isn't there something doing the rounds saying that you should find the problem you're working on in a very specific way? He's a very clever fellow. So let's just invest a little bit of time. State the problem before describing the solution. If I recall correctly, this was a very short paper that I smiled and nodded when I read, but never really went so far as we do now. Say, well, now we got a problem we want to solve. Let's see how Lamport would have us state the problem. Where's it? There we go. Oh, sorry, it took a while because it was a scan. State the problem before describing a solution. After several years of writing papers in computer science, I discovered the basic expository rule embodied in the title of this note. As obvious as this rule may seem, there are fields in which it is seldom observed. Computer networking is one example. Okay, I work in computer networking, so it's a good thing that I had this paper to right my wrongs. A typical paper in such a field is organized as follows: a brief informal statement of the problem, the solution, a statement and proof of the precise correctness and properties satisfied by the solution. But in order to abide by the rule, the following organization should instead be used: a brief informal statement of the problem, the precise correctness conditions required of the solution. Okay. So what he's saying is we need to informally state the problem and then say very specifically what what a correct solution would look like. So what he's telling me is not to just define the solution as the kind of half-baked idea that's been rattling around in my brain, but to actually write down the actual requirements for a solution, and then we come back and see whether this sealed tables is actually the solution. It may be that we've identified the problem correctly, and that there is a good solution, and that sealed tables is not that solution. So I guess that's what we're gonna sealed tables. So the problem and the requirements for a solution. You know, let's end the stream here actually, and let's come back and do this the next time around. We'll define the problem. We did a good brain dump. We can always come back and revisit this, but let's just, since it's a Sunday, let's just stop there. Till next time.